Hello everyone, I would like to start today's lecture about neural networks. So what are neural networks, they are used for? So typically we have a system that's called a black box, and we have some inputs and we want a desired output. However, we don't know what's going on inside that system, so this is unknown for us. But we have the mapping between input and an output. So we know for a fact that if you give a certain input, you produce certain output. So what we can do is actually teach that box to behave accordingly. So neural network, of course, is one of the machine learning algorithms. Can be used for many applications, for pattern recognition specifically, or any other signal processing applications. So the main point is generalization, which means that for certain input you generalize some of the output, and typically what you refer to is by giving a mapping between input and output that typically was not presented during training. So when we say that a neural network has generalized, it's when we produce reasonable outputs for inputs never seen before. Of course, there are many flavors of neural network. There are the supervised learning, that is with a teacher. This means we actually know the outputs for the inputs that we want to try. For example, I know that if I give the letter A to my system in a character recognition problem, say this is a neural network, it will give me the output 0. If I give B, it will give 1, C, 2. So here I'm teaching the neural network to learn that if it encounters letter A, to direct the output to be 1, letter B to direct the output to number 1, and C to number 2, and so forth, going like this. So actually what influenced the creation of a neural network is the human brain. And the human brain is made up of billions of neurons which are connected to each other. So we can just approximate this like something like this and so forth. We have many neurons that are connected to a single neuron. So let's say we have this neuron K, and it's taking input from many other neurons. These neurons are connected with each other using a synapse, which we're going to discuss shortly. So if I want to talk about a model of that neuron K, I can assume I have inputs, so I'm going to just give them names. So it's going to be x1, x2, all the way to xm. Each of them have different influences on the other neuron. So what kind of influences can we impose is we can use a weight. So this weight is the strength of the connection between those two, or how important this input is to that node. So we can give it a weight wk1, wk2, all the way to wkm. And here what we want is we want to sum the response of the input that's coming into that neuron. So we need a combiner, a linear combiner, where it just does the weighted sum. And sometimes we need to bias our network. That is, we want the threshold not to be 0. We want to increase the threshold. and we're going to talk about this shortly, we can add a bias BK, and this will generate what's called the induced local field VK. This is called the induced local field. And then we apply an activation function phi, and then we have the output y of k. This is the output. So if I want to write the mathematical formulation for this model of a neuron k, I can say that, for example, Vk is actually the summation for j equal 1 to m for the sum of the input times the weight. So it's going to be wkj times x of j plus the bias bk, where k denotes the neuron in question. And then the output will be the activation of the induced field Vk. Okay, so here if we look at the model of the neuron, we have the input, we have the weights. The weights are the the strength of the connection between the presynaptic neuron or the neuron before K and actually neuron K. And then we apply a bias and then an activation function just to squash the input between two values, and I'm going to discuss how we can do that. And the output will be the value of the activation function. So now if I want to discuss a little bit the bias, so what is the bias? So the bias is just a way to shift the response of the neuron. So effectively, I'm adding a value. So if I take two neurons, for example, these are the input neurons, this is the output neuron. Output, this is the input. So effectively, when no bias is available, with no bias, this means B of k is equal 0. For example, if I take the value of 1 and 2, and this is, let's say this is 0.5, this is 0.4, what Vk will be equal 0.5 plus 2 times 0.4. This means we have 0.5 plus 0.8, which is 0.13. So here, for me, everything greater than a 0 will makes the neuron fire. Everything less than a 0 will make the neuron not active. What if I want to have a threshold greater than B of k equals 0? Let's say I want here this. Let me put this threshold equals 0. So let's say I want to put the threshold to be a 1. This is better for my network. So how can I do this? So typically, I add a bias bk equal 1. So in this case, if I want to say like everything above 1 will fire, everything less than 1 will not fire. So typically what I can do is, let's find V of k. This will be 0.5 plus 2 times 0.4 plus 1. This will be 1.13. Implies neuron will fire. Okay, so bias is just a way to shift the output to a certain range where I want my threshold to be of a certain value. Now the second part that I want to discuss is actually the activation function. So why do we use an activation function? So first I'm going to talk about a specific neural model. It's called the McCulloch-Pitts neural model. of course, in this neural model, what I have is an activation function that looks like this, a threshold function. So the activation function looks something like this. If I draw it like this, this is 0, this is 1. So I use different color. Okay, so this is phi of v. Okay, so phi of v will be equal to 1 if v is greater or equal to 0, and 0 if v is strictly less than 0. Okay, so this means y of k can take two values, either 1 if v of k is greater or equal to 0, and 0 if v of k is actually less than 0. So if you remember our equation, we have y of k is equal phi of the induced local field v of k. So if we take the same example we did before for the bias, so let's say we have this is 1, this is 2, and then we have this is neuron k, and we have the bias, and this is the output y of k. So here we take the bias to be 1, this is 0.5, this is 0.4. So if I want to calculate v of k, okay, so v of k will be, of course, 0.5 plus 2 times 0.4 plus 1 is going to be 1.13. And then when I have y of k is going to be equal to phi v of k, which is going to be phi 1.13, and this will give me 1, which means 5. Okay, if I have different values, for example, let's say -2, -1, I will have a negative value, and then this means the neuron will not fire. So you see that what the activation function is actually doing is just limiting my values between two values, either on or off. This can be useful in many applications. However, sometimes I need a range of values, so we have a different type of activation function called the sigmoidal activation function. So if I want more options for my output, I can try the sigmoid function, which looks something like this. Okay, so I'm gonna have, it's called the S-shaped function. So this is phi of v. So what this activation function does is that if I have values close to 0, it will give them very low value. So they'll say this is 0, this is 1. And if I have values that are close to 1, it will actually give them a very large value. So what I'm doing is I'm not going with two values, 0, fire or not fire. I have many intermediate values. However, as I decrease my input, the values will be more and more close to 0. As I increase my input, it will be more and more closer to 1. So the function phi of v will be equal 1 over exponential minus AV, where A is how steep our S function will be and how loose our S function is. So typically this activation function is very popular, and it also gives us many range of values. We can also use it for bipolar coordinates. So let's say I want phi of v to be equal to +1 for v greater than 0, 0 for v equal 0, and -1 for v less than 0. I can use, in this case, I have the threshold function will be like this. It's going to be between -1 and 1, and the sigmoid function will be the tangent h function, which is going to be something like this. If I want to discuss some network architecture, so as we said, we have many neurons connected to each other. So some of the network architectures we're going to discuss in these lectures are as follows. So we have the single layer feed forward, which typically involves inputs, okay, and we have one output layer, and typically each neuron is connected to all and also here. So this is a single layer feed forward neural network, usually composed of an input layer and an output layer. We also have a multi-layer feed forward neural network. So we can have multi-layer feed forward neural networks. In this case, I will have, let's say, I'm gonna decrease. Let's say I have hidden layers and an output layer. So each node is actually connected to all the neurons. So here we have a 3-to-1 neural network. We have 3 input layers, 3 nodes. We have 2 nodes in the hidden layer, and we have 1 neuron or 1 node in the output layer. So these 2 types, of course, as we increase the hidden layers, this is what's known as deep learning. So hidden layer actually transforms my input into another space, and I can cascade as much hidden layers as I want, but the risk is actually overfitting your data. So the purpose of the hidden layer and the number of hidden layers will be discussed in later lectures when we talk about learning. Now, if I want to talk about the first neural model that we will see, is called the RosenBlatt neural model, and this RosenBlatt neural model is actually used as a linear separator. So RosenBlatt's Perceptron. So also can be known as mcCulloch-Pitts neuron. So the RosenBlatt perceptron, what was trying to solve is actually finding linear separation between inputs. So this is the simplest form of neural network. So let's say I have a class 1, this is class 1, and this is, let's say, class 2. So I can find a linear separator between the two. So I have, let's say, positive tests and negative tests. I need to classify what are my positive cases, what are the negative cases. Another example can be this a spam email or not a spam email. So I need to, if my system is linearly separable, which means I can draw a line or a hyperplane in multiple dimensions, then this means it's a linearly separable, and then I can use the RosenBlatt perceptron to do this. In other cases, let's say let's say a case where it's non-linearly separable. Let's say I have something like this, and this is gonna go like that. So this is class 1, this is class 2. So you can see that I cannot fit anymore a straight line. So this is non-linearly separable. So in this case, RosenBlatt is not used. Cannot be used because my classes are not linearly separable. So of course I need to know a little bit about my problem that I'm going to solve before actually using the specific neural model that I want to use. So if I take a look at the RosenBlatt perceptron we just discussed it, I'm going to write the model again. So this is the model. So what we have is, of course, we have inputs x1 to xm, and we have, this is w1, this is x2, w2, and then we have wm, and this is, we add another bias b, and then we have the induced local field v, and then we have the hard limiter phi to get the output y. So if I want to write the formula again, p is equal summation I equal 1 to m wi x of I plus b, and of course this is v, and y will be phi of v. Now what this outputs is actually, if I take a two-dimensional problem, so actually what I'm trying to say is that I have a decision problem, something like this. So I have a line, I'm going to call this w1 x1 plus w2 x2 plus b equals 0, and here I have class 1 and here I have class 2. So what the RosenBlatt does is that it trains the network in a way it separates my data into two classes, class 1 and class 2, and when we say that the neuron or the model has learned the classes, is that when we find the equation of this line, which is finding the weights and the bias. So my aim is finding wi and b for my specific data. This is when we say that the network has learned, and now it generalized my data. Now if an input comes from that it has never seen before, it knows that this can go for class 1 or class 2. So now if I want to elaborate more on this idea, or how does it learn, we're going to talk about the perceptron conversion theorem. So the perceptron is the neuron, the neural that we're talking about, the RosenBlatt neuron. It's called the perceptron conversion theorem. So actually, if I want to write my input in a different way, so let's say I have x of n is equal 1 x1 of n x2 of n xm of n transposed. So this is my input, where n denotes the time step in my algorithm, in the algorithm. So now I have a weight Wm. Wn, okay, same time step. We have B, W1 of n, W2 of n, all the way to Wm of n, also transposed. Of course, to make the mathematical formulation more compact, I included the bias. So this is the bias term. And we multiply the bias. We assume that the bias is multiplied by 1 just to add the plus b. So now I can write the v of n in the compact form, which is I equals 0 to m win x I of n. So in this case, I start from 0 because I want to take into account this one, this value. So 0 will take into account the bias. If I want to write it like this, you can, or draw a diagram for that. So we have the axis. So this is the bias, and this will be b. This will be x1, x2, all the way to xm. Of course, I have the weight W1, W2, W3, Wm, and then we have, this is V, and we apply the hard limiter. Hard limiter is my threshold activation function, which is going to be the 0 or 1 signum values. If I want to take bipolar, it can be something like this. Okay, this is my hard limiter. This can be written in compact form as Wt of n x of n, where W will be a matrix that is transposed from W0, W1, and then x0 till x, of course, m here, Wm, and this will be V of n, where n is the iteration, or the where we are going through with the algorithm. Now the solution here is Wt x equals 0. This is the solution that will be linearly separate our two classes. For example, something like this in two-dimensional. It's going to be a hyperplane in another dimension. Now, if I want to elaborate more on the perceptron conversion algorithm in theory, now suppose we have two classes that are linearly separable, and we're trying to find this linear separator, which is the W vector. So what's the learning process? How come it goes to separate those two classes? So first we need to say, if we have Wtx greater than 0, this means x belongs to class 1. If Wtx is less than or equal to 0, then x belongs to class 2. So in this case, we're just separating those two classes. The case where Wtx equals 0, it's arbitrarily chosen to be class 2. It could be class 1 based on our assumption. So how does the algorithm works? So we have two cases. If we supply x to our network and we have a correct classification. So let's talk about the nth iteration. After we supply first, second, third, and we reach our nth iteration. So if x of n is correctly classified, this means I have wn plus 1 equal wn, so no weight update, it's correctly classified, so why do we need to change the weights? It's giving me the correct response. That happens if wtn times x of n is greater than 0, which is the case here. This means x of n belongs to class 1. And same thing for the second case, equal wn if wtn x of n is less than 0 and x of n belongs to class 2. Now, the second case, where we have if x of n is incorrectly classified. This happens when some values x of n should be in class 1, however it is in class 2. Here we need to update the weights, so we need to change the weights. So in this case, the first case, we have w of n plus 1 is equal wn minus eta of n, which is the learning parameter, times x of n. So in this case, we have wt of n times x of n is greater than 0 and x of n belongs to class 2. So if you notice here, when we have class 2, the value should be less than 0. However, we have the greater than 0, and the classification was that it has to go to class 2. So this value should not contribute, or should contribute negatively to the weight, not positively. So in the next case, it's going to be plus eta of n x of n, and you guessed it, if wtn x of n is less than 0 and x of n belongs to class 1. So here wtn x of n is less than 0. However, we wanted to increase it so that it can be correctly classified in class 1. So this is why we add the value of x of n. Here, the learning parameter is just how fast our algorithm is going to operate. We want big steps, we want small steps. So of course, the choice of eta is very important. Let's discuss the learning parameter. Eta. So if eta of n is equal n greater than 0, then it is constant for all iterations, and we have a fixed increment adaptation rule. Now, if given that eta of n is equal 1 for all n, and w0 equals 0, then a solution exists. We call this w0, and this can happen, and it must terminate after a maximum of n max iteration. So the rule says that if these are the cases, then the algorithm terminates after a maximum and eta max iteration. Okay, so now if I go ahead and check the algorithm and the way it operates, so I printed a version of the algorithm and I'm gonna place it here. So given a vector of n plus 1 components, of course we have from x 0 to xm. So this is m plus 1 input, and we have a vector, m plus 1 vector. Of course, we have an output y of n. This is our y, let's put it this way. And of course, these values, and we have, this is the bias, this is b, this is w1, w2, until I reach wm. So we have the bias, and the x0 equal, of course this is going to be equal 1, since this is the bias input. And we have the desired response. For example, let's say I have the input A, I have input, any input, let's say it's doing character recognition, and we say if this happens, then this is going to be y will be 1. If it's something else, any other letter is going to be let's say minus 1. So this is the desired output. Given a set of input, I want the desired output to be 1 if this is the character I want to have. So this is the actual response quantized by the activation function. And then we have the learning parameter. So we initialized all the weight vector by 0. Everything is 0. And then we apply the signum function. We calculate wt times xn. The signum function is as follows. Signum of v will be plus 1 if v is greater than 0, and minus 1 if v is less than or equal to 0. So this is the signum function. Now the adaptation rule, what happens is that we want to adapt based on the difference between the desired output and my actual computed output. So in this case, and it's multiplied by eta, which is now not showing. So wn plus 1 is equal to wn plus dn minus yn times x of n. So as we see here, so we saw that we need to subtract when the value should be less positive and add when we need the value to be more positive. And the way we do this is by closing up the distance between dn and yn, the desired output and the calculated output. So when this tends to go to 0, this means that the algorithm has learned that input and it terminates. So we continue on doing this until no more update happens. So the algorithm stops when we wn plus 1 is equal wn. So this is where there is no more learning happening anymore. In this case, we say that the algorithm has learned our classes. I would like to discuss the batch perceptron algorithm, which involves a little bit of optimization. So in this algorithm, we add the concept of a cost function. And this cost function is as follows. I'm going to call it j of w, which will be summation of x of n belonging to h. I'll discuss what h is. Minus t, x of n, t of n, where h is the set of inputs that are misclassified, or we have wrong classifications. So what we want to do is we want to minimize this function, this cost function. Okay, so the case for where everything is not correctly classified is included in this set. If it does not have anything, then this will be 0, and there's nothing to minimize here. So since this is a cost function, we want to minimize it, and the way we minimize it is using the gradient descent or steepest descent algorithm. So we have we take the derivative the partial derivative of this function. Of course, when we take the partial derivative, the w will be out, and we have x of n dn. And in this case, the partial derivative of w will be the function with respect to w1, the function with respect to w2, and so forth with respect to wm. So now the weight update rule will happen as follows. So this will be equal to Wn minus the learning parameter multiplied by the summation for x belonging to h, which is the misclassifications, times x of n dn. And this is the batch algorithm that works on actually minimizing this cost function, which minimizes the number of misclassification. So it's a different update rule. It works the same as the Perceptron, the Perceptron conversion algorithm, but instead of using this rule, we're going to use this rule, which minimizes those misclassifications.